at notebook page 81, looking at compounds in which we will see a Roman numeral in their name. The Roman numeral's purpose. The Roman numeral represents the oxidation number being used by a transition element. And the transition elements are in groups 3 through 11. The Roman numeral, it is only used in the chemical compound's name. And the Roman numeral value, it represents the value of the oxidation number. So the sequence. So we're going to start with compounds where we are given the name and we will see the Roman numeral and using that information to change it into the formula. So we're going to use the backbones of everything that we have already done. So the first step is to match each name to the correct symbol. So make sure you don't guess on a symbol. If it's an element, check table S. If it's a polyatomic, look at your table E. In order to come up with the correct formula, we have to know oxidation numbers. The Roman numeral in the name, it is the value of the positive charge. Then we need to look up the second partner's oxidation number or charge. If it's an element, find it on the periodic table. If it's a polyatomic ion, look at table E. Once when we have the oxidation numbers, balance those charges. Remember, the sum must equal 0. And once when we have the ratio, write the empirical formula. And remember, the empirical is the lowest whole number ratio. The Roman numerals that we need to be able to utilize in the naming are Roman numerals 1 through 7, so make sure you know those. And this, if you see this Roman numeral 1 in a name, that means that the cation is using a +1. So the Roman numeral's value equals the value of the positive charge. So let's look at 4 examples here. So we have a substance that says copper Roman numeral 2 chloride. So copper is an element, and we would look on table S for its symbol, and we would find that its symbol is Cu. Chloride, it is the anion name of an element that we know as chlorine, and chlorine's symbol is Cl. So we've matched the name to the correct symbols. Now we need oxidation information. This Roman numeral 2, it belongs to the cation. So remember, the order is always cation is shown first in the name and in the formula, followed by the anion. And since it's a Roman numeral 2, that indicates to us that copper is using a +2 charge. The chloride, the element chlorine, we need to find the symbol Cl on the periodic table. And when you look at chlorine on the periodic table, I know that there are a few different oxidation numbers, but it's an anion, so that means it must be using a negative charge, and it only has one choice, which is a -1. So we know that the chloride's using a -1 charge. Now that we have symbols and the charges, now let's utilize the crisscross method to balance the charges and to come up with a ratio. So we take the magnitude of the 2 for the copper and we crisscross that down to become the subscript for the chlorine. We take the magnitude of the chloride's charge and place that as the subscript for the copper. So here we're going to do a little quick check in the math. We have one cation and it contributes a +2 charge. We have 2 anions. They each contribute a -2, so the total negative charge contributed is -2. +2 plus -2, the sum is 0. So those crisscrossed numbers represent the ratio 1 to 2, and that is empirical in nature. So our formula would be CuCl2. When we look at our next example, it has a very similar name to the substance up above. It still has the name copper and chloride in there. So we know copper symbol already is Cu. We know chloride uses the symbol Cl-. The difference in the two names is the Roman numeral. So now we have copper Roman numeral 1 chloride. So that means that the copper is now using a different oxidation number. Roman numeral 1 means it's using a +1 charge. Chloride, still the IDE, it's still the anion, so it is still using a -1 charge. So we utilize the crisscross method, bring the magnitude of the copper's charge and crisscross that down to become the subscript of the chloride's magnitude of its charge, crisscross it down to become the subscript of the copper. And when you do a little bit of math, double checking the sum of your oxidations, one cation and it only contributes a +1 charge. There's only one anion, it contributes a -1 charge. +1 plus -1, the sum is 0. The crisscross numbers, those are the ratio. 1 to 1 is naturally empirical. So our final formula would be CuCl. Take a look at the next example. We have manganese, Roman numeral 4 nitrate. So the first thing that I notice in this name is nitrate, which means I have a polyion. So I need to take a look at table E. And when I look at table E, a single nitrate unit is made up of NO3. I like to put the parentheses around the polyatomic. These 4 atoms, the nitrogen and 3 oxygens, they share a charge of -1 according to table E. Manganese is not on table E, so I know it's an element. So I go to table S and I find that manganese's symbol is capital M, lowercase n. I have this Roman numeral 4. It's manganese 4. So that means that the manganese is using an oxidation state of +4 because the Roman numeral represents the value of the positive charge. I will utilize the crisscross method to figure out the subscripts. So I take the magnitude of the Mn and I cross that down to outside the parentheses of the poly. So telling me I need 4 NO3 units. I take the magnitude of the nitrate's shared charge and make that the subscript for the Mn. So if I do a quick check on the math, 1 cation and it contributes a +4 charge, plus I have 4 anion units. Each one contributes a -1, so collectively they contribute a -4 charge. So +4 plus -4 is 0. The ratio is the crisscross numbers, so the 1 and then the 4 outside the parentheses. 1 to 4 is an empirical ratio. So I would write this as Mn, and I would keep my anion, the poly, in parentheses because its unit is NO3 and I need 4 of those NO3 units. Last example is platinum phosphate. And the first thing I notice is the ATE ending, which tells me I'm working with a polyatomic, so I need to look at information on table E. So when I look on table E, phosphate is represented by PO4, so 1 phosphorus, 4 oxygens, and those 5 atoms share a charge of -3. Platinum is not listed on table E, so I understand it's an element, so I need to go to table S to find its symbol. And when I look on table S, platinum symbol is PT. Now, there's a Roman numeral 2 in this name. The Roman numeral always belongs to the cation, and it tells me that the platinum is using a +2 charge. So now that I have symbols and oxidation numbers, I'm going to use the crisscross method to come up with their ratio. So I take the magnitude of platinum's charge and I crisscross that down outside the parentheses of the PO4. I take the magnitude of the PO4's charge and I crisscross that down to become platinum's subscript. I will do some quick math to make sure my sum is 0. So I have 3 cations. Each one carries a +2 charge, so they contribute a total of +6 to the structure. I have 2 of the phosphates, 2 anions. Each one contributes a -3, so collectively they contribute a -6 to the structure. +6 plus -6 is 0. So my crisscross ratio of 3 to 2 is a reasonable ratio, and it's empirical in nature. So I would write my formula as PT3, because I need 3 platinums. My anion is PO4, and I need 2 of those to balance out the PTs.